Now in this lecture, we shall have a brief preview of how to design the timber monopole. Now in Australia, we can say that there are these, in addition to using the concrete monopoles or steel monopoles, we also use the timber monopoles. So usually they are circular in shape, and we can say that the base is usually embedded. So if we are saying that, let us say the timber monopole height is approximately 20 meter above the ground, then we can say that it is usually in the range of, we can say, divided by 4 or divided by 3, we can say, below the ground, depending on the, we can say, the ground condition here. So if 20 it is 20 meter above the ground, then this timber base is basically 4 meter below the ground also. Now if we just have a, we can say, actual site condition. So let us say we are talking about this particular area here, and on this particular area we shall see it in the Google Maps also. So that is basically the Maryland road, and we want to install a timber monopole here. So that is basically having a different, we can say, terrain conditions also, terrain categories from different, we can say, directions. So if the wind is blowing from this particular direction, then it is having, we can say, a different terrain category. And if the wind is blowing from this particular direction, then it is having a different terrain category. So that also we shall discuss, but we can just have a, a practical, like, picture also. So this is basically the Maryland's New South Wales, the one that we were seeing in the plan in the Google Maps. So in this NSW, we can say that this is basically the timber monopole that we are, going to design right now. And across this road, you can see also a timber monopole here also, but this is just supporting a single wire here. But for this timber monopole, we can say that there are these lot of, we can say, fixtures that are installed on the top to serve the purpose, and there's a lot of wiring also. And if you zoom in, you can see the peg steps also. So these are the small steps which are used to install, or we can say, climb onto the top. And if you go across this particular street itself, you will see that all the, like, monopoles are installed of timber itself. So here also you can see that this monopole is also in, we can say, timber. So the simple principle is that let us say if it is approximately 15 meter above the ground, then it shall be approximately 2.5 to 3 meter below the ground also. So the reason why it is used is that because it is, we can say, eco-friendly also, and it is simple and straightforward to use. So why I'm saying eco-friendly is that because there is this separate, we can say, organization that do, we can say, plant the trees just for this purpose itself. They are not cut from the, we can say, forest or from the, we can say, green areas. They are just planted separately, and it is ensured that we do not reduce the or, we can say, increase the carbon footprint at any cost. So this is, we can say, along this particular street, this whole area, we can say, is timber monopoles are designed. So they are supplying the electricity also. So we have to ensure that in the case of extreme winds, we can say, these timber monopoles should remain intact or on their, we can say, location. So this is also timber monopole here. And in addition to that, they are installing, or we can say, it is supporting a light also. So coming back to the actual question here, so this was a timber monopole that we were, going to target to design with this particular software, Checkpole. So now this is clear. So you do have an idea. So coming back to the structure here, so this material is selected as timber, base is selected as embedded, and shape is selected as circular. Stress grade. Now stress grade is something, we can say, that is language of the timber code itself. So if we are talking about the timber design, so Australian standard itself has a separate code which guides us to design the timber monopole structures. So the code name is ASNZS 7000. So we do have different formulas, and we do have different formulae to check that whether the timber section is safe in bending, shear, torsion, and axial forces. So coming back to the question here, we were first of all targeting the structure. The structure is clear that the height of the structure is 20 meter above the ground and 4 meters below the ground. site we have already finalized that we can go ahead with the marine land state in the New South Wales. After that, we can select importance level as 2, life as 50 years. So region, or we can say wind speed region is basically A2. And ultimate VR can be selected as 45 and serviceability VR can be selected as 37 meter per second. So if either we can keep it on here or we can just simply switch off to have all the directions as one itself. So the advantage is that by selecting one is that what happens is that even if the orientation or the arrangement of the ancillaries or we can say connections on the top of the timber monopole changes, it is not that your full calculation changes. So that is we can say a little bit conservative. After the terrain category, we can see here that from this particular location, it is terrain category 3. It is approximately 2.7, 2.8, 2.9, and 3.03. So, if we are targeting this particular area here, this is basically terrain category 2.5. This is also terrain category 2.5. And if we are talking about this particular area, obviously it is dense and densely populated area, so it is terrain category 3. Similar is the case for these locations also. It is also terrain category 3 and this is also terrain category 3. So after that, we can say about the shielding multiplier also, that is MS. So, the software has calculated the shielding multipliers for, we can say, for all the structures. So it do help us, saving a lot of time if MS is also getting automatically calculated. Or, if you're not comfortable or if you have if you foresee a probability that a structure may not be there after a few years. So in that particular case, you can go ahead with MSS1 itself. Topography shall be, selected as 1 only, but there might be a little bit of slope from a particular direction. So that is why it has been selected as 1.0353. So there might be a possibility that, this level might be a little bit higher as compared to this particular level or lower also. So it all depends on to the actual site condition. So after that, if we are talking about the loading, that is the fixtures that are installed on the top. So we have assumed that first of all, there is this head frame that is installed, 3 into ComScope and 3x2. So that is the typical language if you are a telecommunication engineer. That is, these are the we can say a particular uh, released by a particular company, and these are the we can say trademark or copyrighted like tag names. So we can say that the height of this is approximately considered as 2 meter, and ComScope is basically the tag name. And after that, if we are selecting about this particular arm, the flood light here, so these have been considered as at 13, we can say 14.5 meter and 15.5 meter. Area has been considered 0.54 meter square, and weight has been considered as 25 kg. So, and these are written as floodlights. After that, additional linear area or we can say loading has been considered as 300 kg per running meter for the cable ladder. So NEMA 20C cable ladder, that is also a standard description that is available. And after that, we can just simply do the analysis here. So in the analysis, you can see that basically these were the A01, A02, A03, and A04. And this is basically the cable ladder L01. And on the top of that, we have installed this CBX6, the one that we were discussing earlier. So we can say CBX3 into ComScope. This is basically we can say the ComScope installed on the top. And these are basically the arms. The one that we are seeing here, that is arm 01, arm 02, arm 03, and arm 04. This is basically the ladder which is used to, we can say, install the cables here. So here also, you can see these cables. So these cables, although they are directly anchored, but it is always recommended that you should have a ladder or we can say a simple cable tray type tray, so that this can be simply fixed at its location. So now it is clear, and after that we can run the analysis here. See, in majority of the countries, it is a standard that when we're talking about the monopole design, they are designed with foundations embedded only. It is not that we are designing or installing a base plate here, and then on the bottom of that we are making a pedestal. In most of the countries it is the standard that we do embed this inside the ground. So here we can see that frequency is less than 1 hertz, so obviously we have to do the dynamic analysis here, or we can say that we have to calculate the Cdyn also. So Cdyn for this particular case here is basically changing from 1.083 to, we can say, 1.1938. And after that, if we are talking about the other parameters here, so other parameters are, we can say, bending moment. So bending moment at the bottom is approximately 193 kN meter. That is reducing to 1.45 kN meter on the top. Similarly, the other parameter, that is torsion, that shall be very less, that is in 2.2 kN meter only. Shear force is 17 kilonewton on the bottom and 1 kilonewton on the top. Similarly, axial force is also like 27 kN on the bottom and 2.3 kN on the top. So that is also like very less. Rotation angle, that we can say is a little bit higher here. So 4.32, and that too when the wind is coming from the southwest direction. Deflection here is also like quite high here. That is 777 mm when we are considering the wind from the southwest direction. Utilization here at the bottom is approximately, we can say, 78% at the bottom, and it is going 1.12% on the top. Cdyn we have already considered here, and wind speed that has been considered is basically 39.16 at the base level, 38.55 at the middle level, and 41.13 at the top level. Wind pressure has been considered 0.9201 at the base level, 0.8917 at the upper level, and 1.015 kPa at the top level. Now drag factor for the, we can say, circular shapes, that is fixed as per the code. Drag factor CD, that also we shall discuss in a detail in a separate lecture. But we have already discussed that how fluid flows around the, we can say, either a cylindrical or a spherical objects. So we can say that considering cylindrical objects and considering the Reynolds number for that, it has been given in the code that drag coefficient for cylindrical shape is 1.2. So I hope this calculation is now clear to you. And after that, if we are doing the design, we can just simply open the one with the maximum bending moment. So the bending moment that is coming at the bottom is 193.56, shear is 17.54, and axial is 27.49. Now when we're talking about the, we can say, calculation of second moment of area, or we can say moment of inertia also. So moment of inertia or second moment of area is basically this particular, can calculate with this particular equation. So I can be calculated as, basically we're talking about the I effective. We're not talking about the gross moment of inertia. We're talking about the effective second moment of area. So gross has been multiplied with the factor 0.6. That is as per this particular section of ASNZ is 7000. So after that we can calculate the, check the member capacity also. So member capacity also formula is given as per, we can say, ASNZ is 7000 section F5.1. So as per this section F5.1, this is the formula to calculate the, we can say, member moment capacity. That is phi into F dash P into K1 into K12, and K12P into K20 into K21B into K22 into KD into KZ. So all of these values are given in the code ASNZ section 5.1, and upon the basis of that we can calculate the capacity as 322.37. Now we can say that the one that we are calculating here is basically kn meter 322, and the bending that is coming is 193.56. So we can say that the value is very less as compared to the other. So these F dash P, F dash C, and F dash S are basically, we can say, the effective, we can say, shear bending strength, compression strength, and shear strength. So 80 MPa is the parameter and that has been considered here. That is, and that is again multiplied with the, we can say, sectional modulus. So sectional modulus is basically, we can say, M is I divided by Y. That is half the diameter of the one that we are considering here. And similarly, we can calculate the torsion also. So for torsion, what we are considering here is that we are considering F dash S. And if we are talking about the shear capacity, again, we are talking about the F dash S. And if we are talking about the compression member capacity, we are talking about the F dash C. So whatever values that we are getting, that is first of all multiplied with the strength reduction factor, that is phi, and after that there are the series of the coefficient that are as per the, we can say, nature of the timber material, or we can say the age, or we can say the grain characteristics, or parallel or perpendicular to grain. So all of these parameters to determine all of these different, we can say, values. So on the basis of that, we can see that it is mostly governing in the bending moment itself, where the ratio is 60.04. So compression reduced moment capacity also needs to be calculated, that is phi mi. So what we are considering here is that we're considering the interaction of the bending moment and compression, and here we're considering the interaction of torsion and shear. So considering the interaction, we are getting the maximum ratio of 78.14. So that is what given here in the design analysis. So all of these are different literatures that are referred. So you can read these literatures, but first of all we do have to understand the ASNZ is 7000 and the Australian standard for steel, sorry, for the wind calculation that we have already discussed in detail. So these are the different, we can say, arrangements, and after that we can just simply check the other parameters also. So I hope the the basic concept is now clear to you, that how the timber monopoles are designed and how it is ensured that the wind load is applied correctly. In most of the cases, it is circular in shape, so drag factor CD is most of the cases 1.2. Dynamic Cdyn, that can be calculated as per the, we can say, the head frame size on the top that we already discussed, and we do need to calculate dynamic analysis if the frequency here is less than 1 Hz. So in this case, it is 0.6986.